Hello everyone, my name is Vivin and I'm with the group with Bio, Chris Ben and Semaganda George, and this is our project, Trustworthy Intelligence Simulator for Forecasting Tourism Demand, and I'll be taking you through our project. When you got the background of the introduction of the project, as you can see, tourism is a key contributor to global and local economies, and it drives in GDP and also job creation, and also it leads to infrastructure development. Uh, the objective of our project is to basically develop an intelligent and artificial intelligence simulator that using machine learning and simulation accurately forecast tourism demand in various economies. Uh, as you know, tourism is sensitive to economic shifts and is political instability, environmental changes, and global events that makes it need for accurate forecasting. So that's why we come in with our project to create an artificial intelligence simulator that can forecast and tell the demand of tourism. Also, our objective is adaptability, as we are going to design a system to adjust various scenarios, providing reliable insights for stakeholders to make informed decisions in a dynamic environment. So it will be able to use real-time data uh, when working, so it can help the people in charge of organizing the tourism sector in every economy to make reliable insights, so that they can easily tell the economies, the parts of the economy where they can focus the resources, the reasons why things are happening in the economy, so that they can be able to make good decisions. The literature review, we reviewed several papers that where we had to get basic knowledge on what is going on, what has been done, and we managed to review about 6 papers. The first one with being cloud-based real-time tourism demand forecasting system with deep learning, and their computational problem was there's a need for forecasting solutions to enable timely operations and decision planning. And they suggested a solution of developing a cloud-based architecture using LSTM for real-time, scalable, and accurate tourism demand. Though they are limited by high frequency internet data and they lack integration of offline data. Also, they lack integration of offline data sources for holistic view. We also reviewed another paper, forecasting of short-term tourism demand based on lifetime series crystalline and RSSVM. And their computation problem was inefficient in using single model to predict short-term demand accuracy in fluctuating periods. So they suggest that they could combine time series clustering with LSSVM, reduce overfitting, and capture varied demand patterns effectively. Though they faced a problem because it was complex in analyzing short-term tourist demand due to variation across different time periods. We also reviewed another paper, deep learning framework forecasting tourism demand, and the computational problem was difficult in capturing nonlinear relations in time series data using traditional models, and they utilize LSTM and GRIU to handle nonlinearities in the time series data to improve prediction accuracy. That was the solution they suggested, though they faced a limitation. They could not incorporate external qualitative variables like social or political events in the models. There's also another paper reviewed ambiguous tourism model based on augmented reality, and the computation problem was a lack of real-time context-aware tourism services that adapt dynamically to user preferences. So they suggested a solution of integrating augmented reality and ambiguous computing for real-time context-aware tourism recommendations. They were limited to context awareness without handling external data variations or dynamic changes in the data. Another paper we reviewed was a novel ontology framework supporting model-based tourism recommender. So the computation problem was difficulty in leveraging traditional recommendation systems to generate personalized suggestions. They proposed a TOML framework that integrates ontology and machine learning models like SVM for better recommendations, and they are limited by to handling of real-time dynamic changes in tourism conditions. This affected the visitors' choices, so it was not working as they had intended. Then we also reviewed the management of tourism resources and demand-based neural networks. Their conventional problem was difficulty in managing and forecasting tourism resources using traditional models. So they developed a neural network ensemble models to manage tourism resources and predict demand more effectively. So they were limited to high sensitivity parameter settings, and they were prone also to overfitting of their models. So it was making it unsuitable for dynamic changes. The last paper we reviewed was research on personalized tourism service model based on context awareness. And the computational problem was lack of real-time personalized services considering environmental conditions and user preferences. So they suggested creating a context-aware service model that provided recommendations based on real-time conditions and the user inputs, but they were limited to real-time adaptations, and they didn't consider long-term forecasting or historical data trends. Those are the papers that we reviewed, and we came out with our idea. And this is our computational problem. The challenges, as I had told you, the traditional models, they were struggling with complex interactions among influencing factors. And this was leading inaccurate predictions that were leading to poor decision making. So, and financial issues for the stakeholders. As you know, as I told you, tourism is a sensitive factor, and there is need for precision as effective resource allocation, strategic marketing and infrastructure development rely on precise demand forecasts. So there is need for precisions while allocating resources to various resources so that they can make tourism more so that they can meet the demand. And the current limitations, the traditional methods, and these ones are limited to unvariate time series data, thus difficult in capturing influence of other factors on tourism, hence inaccurate predictions. Also, there's a limitation of data complexity, as it's difficult in learning patterns in multiple data sets. The data sets we have a lot of variables, which are both data types, and it's hard to learn the underlying patterns that these factors are affecting each other. So there's need for precision enhancing prediction. And the solution that we are providing, we propose to develop an artificial intelligence simulator using machine learning and simulation techniques. And the key features, multivariate data analysis. We know about the data being different variables. We also have to do scenario analysis for impact assessment. We also have to do real-time predictions, and then seamless integration via API. The forecasting models that we use, we're going to use ALIMA. That one will be for time series forecasting. It should be able to tell about the stationarity in the data, what data is missing, what impact, what consistencies in the data. Then random forest and gradient boosting, those are machine learning models. Then we also have the profit model for prediction. And then we are going to the simulation environment. We are going to build a simulation using AnyLogic for scenario analysis and impact assessment. So here we are going to build a model in AnyLogic so that if we change the variables, it can be able to tell us how the demand will be affected. And then the evaluation metrics, we shall use mean absolute error, root mean, squared error, and also R squared. And the proposed the other solution will be predictive modeling, as our model will be able to predict the demand, the trend in demand, see what's going on, use the data that we have, and then predict the demand. We're also going to do adaptability for real-time updates. Our novel contributions will be an XI techniques for model transparency and interpretability, then intelligent AI simulator that forecasts tourism demand, then a simulation environment for scenario analysis, and then an accessible API for seamless integration and distribution. The dataset description, we use the dataset from Swiss tourism company, and it had these different variables. The dataset duration was of 10 years for 2007 up to 2016, and it had 3,653 days. The tourism company, there were four tourism companies. One was for accommodation, the other company was transportation services, and then the other one was for leisure facility. Then we had 562 columns, features or target for like the variables that we'll be working with. And there are four target variables, which we have accommodation, transport one, transport two. These transport one and transport two are the different types of transports that tourists use when they visit countries. Maybe ship, or flying. Most of them fly, and others use water. Also, others use road, but we are not targeting that because already they have come to tour. Already they are meeting the demand. And also, the other variable we are targeting is indoor leisure. The explanatory variables, we had the calendar effects. That's day of the week, weekends, month. Then also event data like holidays, vacation, regional events, and all those kind of variables. We also had weather variables in our data set, temperature, sunshine, perception, and wind. All because temperature and all these weather, they also affect the demand of tourism. And also we had other valuable that they are about purpose, why people are visiting. So these ones will help us analyze short-term demand fluctuations, improve forecasting and decision making for tourism stakeholders. We also had 12 missing values in our data, and also Indonesia missing values, and we handled that by ignoring those columns, those rows that had those columns that had missing values. And we had all data types. We had integers, we had floats, we had all data types and strings. We worked with those within the data set. That was the data set we used. And when we got data visualization, we were able to visualize the relevancies between frequency and accommodation. As you can see, we have on the y-axis accommodation capacity, and then on the x-axis we have the frequency of tourism turnout. And as you can see, the highest frequency. Sorry, my battery was running low. The highest tourism turnout was 270, and it took us to be at 87 accommodation, like when they're having the capacity. And also we can see that when they shows that there's a capacity of 5, there are no turnouts, indicating zero frequency. So we also moved on and we drew a histogram of transport, and it was frequency against transport. And also you can see it. It illustrates a distribution of transport, which is skewed with a peak of 2,000. That's the peak here on the histogram. And as you can see on the x-axis, we have values of transport too. And then on the y-axis, we have frequency of observations. Values range from 1,000 to 10,000 with some present. The most common value is 2,000, though it's the largest contributed to the right skew in the distribution. We also went for our heat map. Our heat map, we drew the heat map to see the correlation between all the targeted variables. And as you can see, the red color indicates there is a very strong correlation. And then the blue color represents a very strong negative correlation. Whereas the white color, it shows that there's no correlation, that it's zero, there's no correlation. And as you can see, we are able to, the highest correlation we had was 0.75, and it was the positive correlation that was between temperature and transportation. Also, the negative correlation was between indoor leisure. That was the most negative correlation, like shows that there's the least correlation between indoor leisure and temperature. Also, we had a negative correlation between accommodation and wind. When we move on to the visualization of our methodology, we collected, this is how we are supposed to go on with the project. We are supposed to collect raw data, which we have already collected from the Swiss company, as I had explained. Then we did data pre-processing, as I have been explaining before. Then we also did exploited data analysis, which I explained before. And then we got pre-processed data. Then we went on to model development and training. As I told you, we developed about around 6 models, and we are training them. And then we did model evaluation, as I will show you. Then after that, when we got the accuracy is not yet there, and that's why we are going to do hyperparameter tuning. Then after that, we do explainability of the model and selection, and I'm going to do the explainability below. Then after that, we are going to develop a simulator using AnyLogic, which we have already started on. And then we are going to develop a user interface, and then we shall be able to put the API, develop an API, and then we put the model for deployment. These are the results from the models we developed. We developed 1, 2, 3, 4, 5, 6 models, like I told you. And as you can see, some evaluation metrics don't work on other models, like the MSE, and it works only on the Prophet model. And as you can see, the linear regressor, it has the most, or it's dominating, it has the most accurate results. And we are going to do hyperparameter tuning to improve the performance of all these other models. These are the results from the Aliba model. You can see the manually trained model, and also the automatically trained model. And as you can see, the manually trained model outperforms the automatically trained model. And the residue, if you come to the residue and the part of the residues, you can see that it's a normal residue, and also the density it shows that the Aliba model is performing well. When you go to explainability of some of the models we built, like the linear regressor, the first graph is the line, and as you can see, it's for local explanation of individual factors or individual variables that the model based on to make the decisions it was making during the training and development of the model. And as you can see, the holiday and then weather summary category have in the positive side, and have meaning the model. These linear regressor depended mostly on holiday and weather summer category to make its decisions. And also the sharp shows the high, that shows the variation, or the other variables, and ways as why the model was making these predictions. And as you can see, like the holiday still, the holiday has the most positive feature value, and it shows that it basically depended on the holiday as a variable against all other variables to make the choices, to make the decisions it made. Also, when we move on to the XGB boost, it's another model we developed, and also it still depends on the holiday, and as you can see, some variables are not well, they are not being even followed to make decisions. As you can see, external events, they didn't even follow that to make any decisions, but see, they are still following holidays to make the decisions that they are making according to the results that I showed you. And you can still see holiday is still dominating as an important value, as an important variable, as to why our models are making these decisions they are making. That's it. Thank you, and have a nice day.